Hi everyone, I'm Fred Fu. Today I'll be talking about code completion in Clang-Repl. This is a project of Google Summer Code 2023, mentored by Vasil Vasilev, and we are members of the compiler research team. I'm also a PhD student at Indiana University. So for starters, let's talk a little bit about Clang-Repl, since not everyone here knows what it is. So Clang-Repl is fundamentally a C++ interpreter built upon LLVM compiler pipeline. So it allows C++ programmers to develop C++ programs in an interactive, exploratory manner. Like here, we define a string and we use it as a part of content we print it out to stand output. So what if we want to list all the members of the variable with a single tab here? So this is where CodeCompletion comes in handy. So what we have achieved in this project? So when LLVM 18 is released, we'll be able to complete a rather long class name when you want to create an instance of it. For example, here you have the class from LLDB called module pointer and offset less than function pointer. And you can simply type mo and then you hit tab. Then you get the rest completed. So in the near future, you will have a more precise completion results. Here we have two numbers and two strings and a generic function called pick1. Since the types of its two arguments need to be compatible, and we already used number one at the call site. If we hit a tab, the completion system shows number one and number two. So in a nutshell, in this project, we overcame challenges of reusing existing Clang semantic code completion infrastructure to implement code completion in REPL. Now let's talk a little bit about the challenges we have faced. So one challenge we faced is that the code completion system couldn't see the declarations defined before the current line. To illustrate the problem here, we compare code completion in regular file and with that in REPL using the same content. The difference here is that the code completion system can see all the declaration defined in the file, but in REPL, it cannot see any declarations defined before the current line. So why does code completion system fail to do so? So a file is basically a single translation unit enclosed by one ASD context. However, in REPL, it contains multiple partial translation units enclosed by two ASD contexts. So to solve this issue, we resorted to two methods, set external source of ASD context and the import method of ASD importer. Using the example here, first we make the main ASD context an external source of the current one. Next, we import each declaration that we have defined so far from the main context to the current one. First number 3, then number 2, then number 1. The other challenge we faced is how to do code completion for top-level expressions. The challenge really comes down to the fact top-level expressions are syntactically invalid in regular C++ file. Whereas top-level expressions are bread and butter in REPL. So as shown in this example here, so the completion system fails to provide none as a candidate in the beginning because the completion context is top level and any identifiers are hidden. So the solution is quite straightforward. We simply added a new completion context kind. And now if we hit tab, and the rest of them gets completed. So now let's move on to semantic code completion. In order to allow it to happen, we would like to know the following information. So like what context is the cursor in when we hit tab, and how can we get the type with respect to the cursor position. And the solution really boils down to several structures used in semantic modules. So the most important one is called code completion context. Using its method getKind, we are able to tell what kind of code completion context we are in, and with the type obtained from the get preferred type, we can use it to like filter code completion candidates. As in this case, since name1 is a string, and therefore the second argument also has to be a string. Furthermore, we can use the method getBaseType to get the type of the expression before the dot. Like in this case, once we know the variable before the dot is a car instance, it's quite easy to figure out all its public members. So now let's talk a little bit about implementation. So our first approach actually closely followed how building code completion works. Like first, we create an incremental compiler instance. Next, we do a bunch of configurations, among which we set code completion point and create our completion consumer. Then we prepare a syntax-only action for parsing and enable code completion in the beginning of the parsing. Finally, when we reach the code completion point, the method process complete results gets invoked. The problem with this approach is we had to write too much code. But luckily, after some digging, we found the AST unit as our current solution. First, we create an AST unit from incremental compiler instance. Then we invoke its method code complete with proper arguments. Then we let it do heavy lifting jobs for us under the hood. And in the end, our method process complete results gets invoked. So to sum up, so basically we solved the visibility issue with some building structure like AST importer and external source. We also enable code completion in top-level expression by adding a new completion context kind. Finally, we leverage semantic modules to achieve semantic code completions, and we are able to pull all this off with a very concise implementation that contains minimal invasive changes. Thank you.
So we've got a couple minutes for questions. Yeah, we have a couple minutes for questions. So if you have any, please come to the microphone in the center of the room, either of the two microphones in the center of the room, and ask your questions.
Did you try to use Clang-D for this?
Actually, I took a hard look at Clang-D, but we can't actually reuse their code for some technical reasons, like because Clang-D care about a lot of fancy stuff, but in our case, we only care about right now. We are trying to do, like, let's say, way less things, way fewer things than Clang-D does.
All right, let's give another hand to our speaker.